For today's lesson, we will be discussing about the continuity of a function on an interval. So, during our last discussion, we discussed about the continuity of a function and how to determine if a function is continuous on a given point. So, this time, we will discuss how to identify if a function is continuous on an interval. So a function is continuous on an interval if and only if we can trace the graph of a function without lifting our pen on the given interval. So we still have this property wherein if we trace the graph, then we should trace it without lifting our pen, or there should be no gaps, no breaks, or holes in our function on the given interval. So when we say interval, last time we only consider one point. This time, if the given is an interval, that means we have set of points. For example, from 5 to 8. So we will check if the function is continuous at this given interval. So the values of x involved now is from 5 to 8, but they are not included. So we'll discuss first the different types of interval because we have different types of interval. So we'll discuss them one by one and we'll have examples. So we have what we call as the finite interval. These are intervals whose endpoints are bounded. So when you say finite interval, that means we have endpoints, or there are boundaries. So the first kind of finite interval is what we call as the open interval. So in open interval, this means that our boundaries are not included. So we use A not included up to B not included. Or we can say that x is greater than A but less than B. So an example of this will be 2, 5. So that means we will be considering the values of x from 2 to 5, but the boundaries are not included, or 2 and 5 are not included. We also have what we call as the closed interval. So in this case, the boundaries are included. So it's part of our values of x to consider. So x is greater than or equal to A, but less than or equal to B. So for example, let's use 2, 5 again. But this time, 2 and 5 are both included. So the boundaries again are included for closed interval. And we have combination. So composed of an open and closed interval on either side. So it can be like this: A is included up to B not included. So x is greater than or equal to A but less than B. So only one side of our interval or one boundary is included. So let's say we have 2 included up to 5 not included. So in this kind of interval, the boundary 2 is included in our set of values of x to consider, and then 5, which is the other boundary, is not included. Or it can also be like this: A not included up to B included, or x is greater than A but less than or equal to B. So this time, 2 is not included, then up to 5 included. So this is again what we call as the finite intervals. So these are intervals whose bounded or whose endpoints are bounded, or simply if we have boundaries or endpoints. Then we have what we call as the infinite interval. So for infinite interval, these are intervals with at least one unbounded side. So you can think of it as only one side of it has an endpoint. So we have open left bounded. So open left bounded means that the left side of our interval is or has an endpoint. So let's say it's A up to positive infinity. So let's say this is your number line and then this is A. So from that A going to positive infinity. But A here is not included. So that's why we call it as the open left bounded. Or we can say that x, the values of x to consider are greater than A. And then we also have the closed left bounded. So in this case, it's the same as with the first one, but this time the boundaries are included. So for example, I have 2 included up to positive infinity. So from 2 going to the right, going to the positive infinity, wherein 2 is also included. So that will be x is greater than or equal to A. And then we have open right bounded. So in this case, the boundary now is on the right side, and there is no boundary going to the left or going to the negative infinity. So that's why it's negative infinity to b. So let's say this is your number line, this is b, so this is the starting point, and then going to the left, going to negative infinity. So that can be x is less than b. So here it's open, so that means the boundary on the right side is not included. And we also have the closed right bounded. So in this case, it's the same as the third one, but this time the boundary, which is b, is included. So x is less than or equal to b. And then lastly, we have what we call as unbounded. So in this case, there's no boundaries at all. So it extends from negative infinity to positive infinity. And that means we are considering set of all real numbers for the values of x. So again, these are the infinite intervals. So there should be at least one unbounded side, or we can call it unbounded if there's no boundaries at all. So now let's try to determine the continuity of the given graph in each of the given intervals. So I have here a graph, and then all we have to do is just to determine if it's continuous on the different set of intervals. So let's start with this example. This is the graph, and then we have 1, 2 included. So this one is a closed interval. So we have boundaries, and the boundaries are included. So for you to identify if the graph is continuous at this given interval, then we have to identify first where are the boundaries, or where is our function given these values of x. So we will start from x equals 1 up to x equals 2. So you can just look at the x-axis first. So this is x equals 1, this is x equals 2. Now where is our graph if x is equal to 1 and if x is equal to 2? Again, take note, the boundaries should be included. So all you have to do is just to look at the graph. So here, you will see for x equals 1, we have two choices. We have this and this one right here. So one is a shaded circle, the other one is unshaded. And from our discussion last time, if there is an unshaded part in a graph, that means that part is not included in our domain, or it's not included in the graph. So since here x is equal to 1, we want 1 to be included in our function. So from the two of them, what we will choose is this one right here. So again, what we will choose is this point, since at this point right here, x is included. So we will not choose this, because if we will choose this point right here, or this part of the graph, it means that x is not included, or x equals 1 is not included, because it's a hollow circle. So that's why we're using this. So that is for x equals 1. Now, for x equals 2, so all you have to do is to look up here, and then we will reach this point. So let's shade this, because x equals 2 should be included. Now, after you identify the boundaries of our interval, next is you have to check if you can trace the graph from the first boundary going to the other one without lifting your pen. So start at this point. You will see that I have to jump. So from there, I have to jump here so that I can go to this point. So I can go straight to x equals 2. Since there is a gap or a break here at this part, so that means our function is discontinuous. So discontinuous on the interval 1, 2 included. So that is how you can check if it's continuous or not. You have to identify first the boundaries. Where are the boundaries? And then check if you can trace the graph without lifting your pen. Next, let's try to check if it's continuous on the given interval 1, 2, but this time it's not included. So this one is an open interval. So same thing, we have to identify where is x equals 1 and x equals 2, because those are our boundaries. But we have to take note that those boundaries should not be part, or they are not included when we will check. So this is x equals 1, this is x equals 2. Now, since the boundaries are not included, so that means from this 2, from these 2 points, from x equals 1, I have to choose this point right here. So this will be my boundary because again, x equals 1 is not included. Because if I choose this point, that means x here is included or x equals 1 is included. So again, I'm choosing this because it is not included. And then for 2, so again, you just have to go up here and then here. This point right here. So this is where x is equal to 2. Again, the boundaries are not included. So let's check. So from this point going to the other point, so I can trace it without lifting my pen. So there's no breaks or holes. Therefore, the function is continuous on the interval 1, 2. Next, how about if it's 1 not included up to 2 included? So, same thing. So, we have to look at x equals 1. But, x equals 1 should not be included. So, I will use this point right here. Up to 2 included. So, this point right here. So, this is where x is equal to 1. And then this is where x is equal to 2. So, again, I have to trace without lifting my pen. So, there. So, I can trace it. Therefore, the graph is continuous on the interval 1, 2 included. Another one, let's say we have 1 included up to 2 not included. So since 1 here, for the value of x is included, so I have to use this point right here. So this is where x is equal to 1, and that is where x is equal to 1 is included in our graph. And then 2 not included, so I just have to create a hollow circle there. So this is where x equals 2 is. Now I have to trace it again, but since, as we can see, there is again a gap here before I can go to x equals 2. So therefore, this is discontinuous on the interval 1, 2. Next, let's have from 1 going to positive infinity. But this one is, the boundary is not included. So, we have 1 not included, so we will be using this point. Now for positive infinity, since it goes to this side, this is where positive infinity is going for the value of x. Therefore, our graph, so we will just follow our graph, so it goes like here also. So our graph goes to this direction as the value of x goes to negative, or as our value of x goes to positive infinity. So since I will start at this point, so I can trace it without lifting my pen going to positive infinity. Therefore, our graph is continuous on the interval 1 not included up to positive infinity. Next, if we have 1 included going to positive infinity, so this time I will be considering this point again. I'm using this because this is where x is equal to 1 and 1 should be included. And then again, going to positive infinity, so on this side. And since there is again a gap, there's a gap here before I can go to positive infinity. So it shows discontinuity at that part. So therefore, this function is discontinuous on the interval 1 included up to positive infinity. And then next, let's say we have from negative infinity going to 1 not included. So 1 here is this one. We'll be using this because again, the boundary is not included. So I'm going to use that point. And then, next is going to negative infinity. So, the negative infinity is going to the left, so on this side. So, as our value of x, as our value of x goes to negative infinity, our graph goes at this direction. So, that is going to negative infinity. So, from this point going to that side, you will see that there is a gap. So, there's a gap, and then before we can go there. So, that means our function is discontinuous on the interval negative infinity up to 1 not included. And let's say we have here 1. 1 is now included. So I will be using here this point right there. So that is x equals 1. Again, I'm using this because 1 should be included. And then going to negative infinity. So going there. So from that point, going to negative infinity still, there's no gaps or breaks. So we can say that it is continuous on the interval negative infinity to 1 included. And lastly, it's now going to negative infinity to positive infinity. Since what we know, if it's unbounded like that, that means we have to consider all of the values of x. So since here we have a gap, so there is a gap in our graph, that means our function is discontinuous. Because you cannot graph it or you cannot trace it without lifting your pen from negative infinity going to positive infinity without lifting our pen, because we have to cross this gap right here. So our function is discontinuous on the interval negative infinity to positive infinity. If we are given the function and we have to determine if it's continuous or not, so these are the two things that we have to remember. So if the interval is an open interval, so to check the continuity of that, then we have to check if it's continuous for any real number on that interval. So how are we going to check if it's continuous on any real number on that given interval? So for example, the interval given to us is 3 to 5, not included, so it's an open interval. So you have to check, will it be continuous for all those numbers between 3 to 5, or can I get a value for our function if we substitute the values from 3 to 5 there? So if you cannot identify any restriction, then that means it is continuous on that given interval. Now, if the interval is closed, or it's a closed interval, a function f is continuous if it is continuous on AB not included. So we have to check first if it's continuous on the open interval AB, and we have to get two limits. So first is we have to check if the limit of f of x as x approaches a from the right is equal with f of a. And the other one is we also have to check if the limit of f of x as x approaches b from the left is equal with f of b. So these are three things that we have to consider if the given is a closed interval. So first, you check if it's continuous on an open interval AB. Next, you have to get the limit of f of x as x approaches a from the right and check if it's equal with f of a. And then last, get the limit of f of x as x approaches b from the left, and it should be equal with f of b. Now, let's try to determine if the given function is continuous on 2, 5 included. So first thing that we have to do is to check. So first, check if continuous on 2, 5. So we're checking if it's continuous on the open interval. So we just have to change the symbols here. By the way, this is A and then this is B. Now to check, so we have to identify, since this one is a piecewise function, we have to identify which sub-function to use. Since we have to check if it's continuous on the interval 2, 5, that means the values of x that we have to use should be from 2 to 5. But again, 5 is not included and also 2 is not included since it's an open interval. So what are the values from 2 to 5? We have 3, we have 4, we have 2.5, we have 4.5, and so on. So if we will look at our sub-functions, so we have here x is less than 5. So we will use 2x minus 1 if the value of x that we're considering are less than 5. We'll use x squared if the value of x that we are using or going to use are greater than or equal to 5. But since what we want are just the values from 2 to 5 and they are still not included, that means it will fall under this category or this subfunction, which is 2x minus 1. Because those values from 2 to 5 not included are considered less than 5. So we'll be using f of x equals 2x minus 1. Now, we have to check, will it be continuous for all the values in our given interval at this given function? So, since this one is this is a linear function, anything that you substitute here, you will get a particular value. Because again, it's linear, the domain of a linear function is set of all real numbers. So, that means it will be continuous for any number. So, since it's linear, so we can write here, since it is linear, it is continuous for all real numbers. So, therefore, we can say that the function f of x is continuous at 2, 5 not included. So, we're done checking with the first one. If in case it is not a linear equation or function, so you can try to solve for the restrictions or what are the restricted values wherein we cannot get a particular value of a function if we substitute that given value of x. Next, after checking, it's already continuous. Let's go to the next one. We have to check if the limit of f of x as x approaches a from the right is equal with f of a. So, our limit here, limit of f of x as x approaches a, our a is 2, so 2 from the right. And then later, we will check also f of 2. So, we have to check if they are equal. Now, for the limit of f of x, since what we want is from the right of 2. So, if we're going to think for the values of x from the right of 2, so that means those are 2.1, 2.001, 2.010, 2.015, and so on. So, values that are greater than 2, but we're just considering the values that are closer or the closest to 2, closest as possible. So we have to use again the first interval. So we're going to use this because those values of x is under this category or this subfunction, which is less than 5 only. So we're going to use this 2x minus 1. And since this is a linear function, as what we discussed last time using limits of algebraic function, so we can just do direct substitution. So 2 times 2 minus 1. So we have 4 minus 1, which is 3. So this is now the limit of our function as x approaches 2 from the right. Now, if we're going to solve for f of 2, so that means we have to evaluate our function at x equals 2. So we'll be using again the first subfunction because that is our value of x is less than 5. So 2 times 2 minus 1. So we again have 3. So as you can see, the limit of f of x as x approaches a from the right is equal with our f of a. So we're done with the second condition. And last is we have to check if the limit of our f of x as x approaches b from the left is equal with f of b. So we have there limit of f of x as x approaches our b is 5, so 5 from the left. And we also have to check f of 5. Now let's solve for the limit. Since what we want is to solve for the limit of the function as x approaches 5 from the left. So from the left of 5. So what are those numbers? We can have 4.5, 4.999, 4.998. So if we will look at the given conditions here, we have x is less than 5, x is greater than or equal to 5. Since what we want are the values from the left of 5, that means it should be less than 5. So we will be using this subfunction again. 2x minus 1. So 2x minus 1. And again, since this is linear, we can just do direct substitution. So 2 times 5 minus 1. So we have 10 minus 1 is 9. And then last is we have to solve for f of 5. Now this time x is equal to 5. So if x is equal to 5, that means it will fall at the second subfunction, which is this one, x squared. So we will be using that. So we have here x squared. So substitute. So that will be 5 squared or 25. Now as you notice, the function or the limit of our function is not equal with the value of the function if x is equal to 5. So it failed to satisfy this third condition. So that means we can now conclude that this function is discontinuous on the interval 2, 5 included. So that will be our conclusion again because it failed to satisfy the third condition, which is the limit of f of x should be, as x approaches b from the left, should be equal with f of b. Okay, so again, if it failed to satisfy one of the conditions, you can say that the function is discontinuous on that given interval. So that's it for today. I hope you learned something about the continuity of a function on a given interval using the graph and also using the function itself, and see you next time.